I'm Steve in IT, and I'm a network engineer specialized in network security, automation, and monitoring. This time we're discussing Layer 2 in an overview of the data link layer. Throughout this series, we're going to talk about the technologies, tools, threats, and workflows involved in network forensics. When we talked about physical Layer 1 attacks and forensics, I talked about how, by nature, Layer 1 attacks and the investigation of them pretty much need to be conducted in person. Well, except for access logs and camera footage. As we move into Layer 2 of the OSI model, the data link layer, this changes for better and for much worse. As the investigator, a plethora of tools exist for the discovery and analysis of Layer 2 attacks. But this is also the lowest layer of attack in which an attacker can attempt exploits remotely. We aren't quite into the easy access zone for attackers, though. We'll need to talk about Layer 2 and the two most prominent technologies to explain why. In the 1970s, Xerox had a problem. Every time a Xerox product created packets, they would fly off in a random direction, never to be seen again. That's why the folks at Xerox created MAC addresses. Well, that's not completely true, but Xerox did create the convention and utility around MAC addresses in the 1970s. Is it too soon to stop calling them the 70s, since we're halfway to the next 70s? Anyways, the IEEE 802.3 working group, the IETF, multiple other working groups, and many vendors have contributed to the development of the MAC address standard ever since. So what is it? In short, Media Access Control, or MAC, is the technology used by networks to give physical Ethernet interfaces a logical association, called a MAC address. Now that you have some idea of what MAC addresses are, let's quickly talk about what they look like. Ethernet interface MAC addresses are unique 12-character hexadecimal colon-separated, well, sometimes dash, identifiers. They look like this. Every Ethernet interface gets its own unique MAC address, denoting the organization who created that interface, which we can reveal in the first 6 characters, called the OUI, or Organizationally Unique Identifier. You can look up the OUI to see who made, like made in a factory, that specific interface. The second half of a MAC address is called the Extended Identifier, and it's intended to make that MAC address truly unique. The entire MAC address is coded into the non-volatile read-only memory of that network interface, and this unique interface identifier is called the burned-in MAC, though you won't hear that term too often. So why do I keep calling out unique like that? Well, because there are exceptions caused by how MAC addresses are handled, some intended and some nefarious, which takes us to the Ethernet protocol. The Ethernet protocol isn't just a protocol. It's a whole suite of technologies, standards, and other protocols that work together to make the common types of data networking possible. We call it a protocol, but if you want to be pedantic, and I do, it's a protocol suite or standard. The Ethernet protocol straddles Layer 1 and Layer 2 of the OSI model, but we've already talked about Layer 1 in enough detail. What we're more interested in is how the Ethernet protocol handles MAC addresses, firmly in Layer 2. And in short, Ethernet dictates that a packet should be handled at Layer 2 such that network devices forward the packet from the packet's source MAC address to the packet's destination MAC address. Ethernet does more than simply providing direction, also prescribing how packets should avoid colliding with each other on the network, standardizing link speeds at Layer 2, and providing error checking to validate the integrity of a packet. The part of a packet containing the Ethernet details, including the source and destination MAC address, is called the frame. The terms frame and packet are commonly used interchangeably, but more technically, frame refers to the Layer 2 wrapper, a frame, around a Layer 3 packet, much like a physical frame around a photo. And frames don't cross Layer 3 boundaries, meaning that source and destination MAC addresses can't traverse from one subnet or VLAN to another intact. We call the boundary in which a MAC address is confined a Layer 2 domain. This is what typically limits the reach of most Layer 2 attacks, with exceptions for things like VLAN hopping attacks. Since MAC addresses cannot leave a Layer 2 domain, the source and destination MAC address will be rewritten by each Layer 3 gateway hop by hop, with new frames per hop shuttling the IP packet along its layer 3 path. We'll talk about that in another video in more detail. Well, what if I want to send a packet to multiple destinations at the same time? Well, do I have good news for you? You can. Well, kinda. You just have to mess around with it a bit. Literally. Bit 0 of the first octet of the MAC address. If you leave that bit set to 0, you have a Unicast MAC address, which isn't going to help you hit a bunch of destinations at the same time, because Unicast is a directionality. It means that frames can only go to a single destination MAC address. Burn-in MAC addresses are Unicast addresses. There are two more directionalities of MAC addresses, multicast and broadcast. Multicast addresses are kind of like a whitelist for network traffic that an interface wants to listen to beyond its unique Unicast MAC address. While they have many utilities, multicast MAC addresses are often used for sending the same media in a data stream to many different endpoints, like video conferencing systems, dynamic display screens, or IPTV. Some well-known multicast addresses serve network functions, but they still follow the same behavior. While Unicast addresses have the least significant bit, bit 0, set to 0, the least significant bit in a multicast MAC address is set to 1, which we see in the image. When I say the least significant bit, that refers to the lowest value bit in a field. In this case, that's bit 0 on the first octet of the MAC address. Broadcast addresses are similar. Actually, they're even technically also multicast addresses, in that these messages also propagate out across a network, but unlike a proper multicast address, broadcast addresses are used when every receiving interface should process the message. Layer 2 broadcasts are also sent out with that bit set to 1 like a multicast address, but further having all bits set to 1, or all hexadecimal Fs. Broadcast addresses are only used for network utilities or for suspicious purposes. Now, I didn't throw it up here, but virtual MAC addresses on the network interfaces of virtual machines and containers can also be unwittingly reused, but that's normally fine as long as two reused MACs aren't on the same subnet or VLAN, and they're not blocked by a network access controller for being a doubled MAC. All right, let's get into a demonstration. And this code we're going to use is available on the GitHub repo for this course, which is linked in the video description and on my website. All right, I'm going to pop up a couple of PuTTY terminals, and we're going to play with MAC addresses in real time. We're going to start SCAPI on both of them in sudoer mode. And SCAPI does need sudoer permissions to do a lot of its functions, so keep that in mind if you're ever seeing errors. And SCAPI does need sudoer permission to perform a lot of its functions, so keep that in mind if you're seeing errors. I have this code accessible in the history, but we're going to go through it real quick. On the left, SCAPI is sniffing traffic and printing the source and destination MAC address of the packets that are traversing the machine's Ethernet 0 interface, while filtering just for the ARP packets. And this machine is it's a Raspberry Pi that's running Parrot's version of their Light OS. And on the right, the code is constructing an ARP who has request packet with the spoofed MAC address of 00, 11, 22, 33, 44, 55. Say that 5 times fast. So right away we can see a hit. That source MAC address does not belong to this machine. This attack, called ARP poisoning, falsely links the spoofed source MAC to the spoofed source IP of 192.168.0.20. These kind of attacks can be used as denial of service or to redirect traffic to the attacker or wherever the attacker wants to send it. Now I'm going to increase the interval just a bit so that we can see a trend change. All right, we'll let that run for a second. Like I was saying, this MAC address does not belong to this machine. So let's go take a look at where we can find those sources of truth for these spoofed packets. Pulling up my TP-Link Omada dashboard, we can see the device table for my Omada switch. I've already filtered in for that MAC address, but let's hit this entry. And we see, of course, that MAC address, We haven't derived a hostname or an IP address, at least not at that switch port. And we can see the network it's on and the uptime. We can also see the switch port, which would be port 14 on a switch that I've named Strider. And even cooler, we can hop into the extra hop sensor in my lab and look up this device. There we see it. I've already renamed it Spoofed Mac as I've been playing around with it. But from a high level, we can see that it thinks that MAC address belongs to a SIMsys device. We can see the IP address derived from the packet. We can see the MAC address that we were looking for. We can see when it was first seen by the extra hop, and we can see the traffic out. Since all I'm doing with that spoofed MAC address is sending ARPs, it's not going to be very much traffic. These charts aren't going to populate anything because they specifically refer to layer 7 protocols. But we can hop over to the network tab, which is going to give us more granular visibility. Here we can see the trend highlight a bit more. And if we scroll down, we can see our ARP packets being sent from that spoofed MAC address. If we click in on that, we can do a create chart from, and there's our trend. This is when the code was running. I think I had it baselining at like a random number between 1 and 30 seconds for how often it should send an ARP out. And then here's where I switched it from a random number between 1 and 2 seconds, which is a much higher rate. Now looking back at that suspicious MAC address, XROP is deriving that, of course, from the OUI. But the most well-known OUI lookup tool is probably Wireshark's OUI lookup tool. Every network engineer knows this. I would argue that probably every cybersecurity analyst knows this as well. Grab a MAC address, pop it into the OUI search, and hit find. And that's checking against the MAC address registry lists, returning SIMsys Inc. And while talking about the idea of suspicious MAC addresses, attackers have been known to use randomized MAC addresses, and while choosing a legitimate OUI can help an attacker blend in, like from a Cisco device or something, a random MAC may unwittingly set the OUI to a manufacturer that would never be on your network in the first place. This MAC, for example, comes from an industrial CAD company that now seems to specialize in dental manufacturing equipment. Unfortunately for them, that specific source MAC is also used by people all the time for testing Ethernet code. Now, I wouldn't call that like a critical investigation step as much as it's a reminder that critical thinking in general belongs in your forensic toolset. MAC spoofing is what I'd call a quiet yet common attack. So it isn't easy to find a lot of modern examples of this attack in the news. It can be leveraged for direct attacks in denial of service and man-in-the-middle attacks, but these have a large footprint and are often caught by even minimally capable security controls. Anecdotally, I'd argue that Ethernet attacks, including MAC spoofing, are more commonly used as an attack vector or in network reconnaissance. Address spoofing can be caught and stopped in multiple ways. Switch port security is the first line of defense, with the most stringent implementations binding a single host MAC address to its connected switch port until a network administrator clears that binding. If any other address tries to connect to that port, the switch disables the port, fires an alert to administrators, or both. Unfortunately, if the attacker knows the permitted MAC, the attacker can spoof it. Strict switch port security can also be very cumbersome to administer, which is where network access controllers, or NACs, like Cisco ICE, Aruba ClearPass, and Forescout excel. These technologies implement, among else, 802.1x port-based network access control. NACs collect data from both endpoints and the network and use these data to ensure an endpoint has an authoritative relationship with the correct MAC address and IP address and is on the correct part of the network, often after checking that a device is authentic, compliant, and malware-free. Since NACs have an inventory of the devices that should be on the network, and also often the behavior of those devices, NACs can block or quarantine unauthorized or spoofed MAC addresses when unusual activity is detected. Layer 2 network forensics relies heavily on logs from NACs and network appliances, which capture both normal operations and suspicious activities. We're going to walk through a scenario with the benefit of hindsight, and then also as the cybersecurity professional. Imagine a company produces widgets in their factory. And let's also suppose an attacker has derived the MAC address and IP of a laptop used in human resources by successfully impersonating an IT pro who just needed to update a few things. If that compromised MAC address suddenly shows up connected to a switch out on the factory floor, it's pretty safe to say that Ron from HR isn't unplugging machinery connections to get a faster internet connection. Instead, we probably have a compromised PLC controller that the attacker is trying to use to get into the HR network. Instead of reconfiguring the switch port for HR use, which many NACs can do, the NAC triggers a policy based on unusual activity, disconnects the compromised PLC from the network, and alerts the cybersecurity team to the incident. Now, going through that scenario as the cybersecurity pro, imagine a SOC analyst is alerted of an HR laptop's MAC address connecting to the network switch on the factory floor where it doesn't belong, triggering a port disable policy in the NAC. Upon investigation, Ron from HR says someone from IT called him and performed remote updates on his laptop. That's valuable human intelligence. As you can tell from the photo, Ron is shocked that it wasn't really IT calling him. Now, based on the NAC logs and the switch logs, we can see that the factory machine's PLC is located connected to the now disabled switch port. The investigator digs into that PLC and finds evidence of the altered MAC address and malware used for discrete file theft and exfiltration. Great job, NAC. Great job, security team, but it's probably time for Ron to redo his security compliance training. Now, NAC logs are forensically interesting whether an attack is successfully stopped, such as in the example case, or also if the attacker is able to defeat the NAC and get in. In the latter case, reviewing the NAC logs and logs and device tables on network appliances can help a forensic specialist inform the network security team on remediating that attack vector. Now that we have an idea of how MAC addresses and Ethernet work, we can think through what I said at the beginning, about how attackers aren't in the easy access zone yet. Well, for starters, a layer 2 compromise alone can't go beyond the single subnet or VLAN, which again we call that layer 2 domain, in which it started. It would need to be paired with a layer 3 attack for that level of network mobility. That's why soon we're going to talk about ARP, DHCP, and different kinds of spoofing in detail. Further, implementing proper security posture on network appliances with port security and network access control will thwart many layer 2 attacks. With that proper implementation, your time investigating layer 2 network attacks will be spent in support of communicating successes rather than failures.